Hello, everyone. Welcome. I am delighted to welcome you to our second webinar of the ASHRAE Technical Committee 6.7 Solar and Other Renewables sponsored webinar series. I'm Ana Maria Segunes, and I'm currently serving as the Membership and Outreach Subcommittee Chair. So today we have the pleasure of having with us Mr. Khalid Nagidi, who will be giving us a presentation on solar-assisted electric vehicles. But before we move into that, I would like to first mention for our participants that if you wish to join TC6.7, I will be posting a link in the comments. You are more than welcome to register and participate in our activities as a technical committee in the solar and other renewable energies. Our next two technical committee meetings will take place during the ASHRAE annual conference in Indianapolis, which starts, sorry, I just got... Okay, sorry, John is giving. So our next sorry, let me know if it's better the sound, John is. So our next two meetings will take place in June 22 till June 26 in the annual conference in Indianapolis. The meetings are typically in hybrid mode, so will be able to participate either in person or online. But going back to today's event, I would like to introduce our speaker, Mr. Khalid Nagidi. Mr. Nagidi is the founder of Energy Management Consulting Group, EMCG, with over 30 years of experience in the design of efficient building services for a variety of new and existing facility types and scales. Mr. Nagidi is also an active member of numerous engineering and industry organizations, including ASHRAE, AEE, and USGBC. He has served as a past chair of the ASHRAE TC6.7 and is also a past expert member of the IA Task 48 on quality assurance and support measures for solar cooling. So for any questions or comments you may have, please leave a comment in the chat and we will have a dedicated Q&A and discussion session at the end of the presentation, and Mr. Najidi will respond to any questions or comments you will have. So without further ado, Khalid, the floor is yours.
Morning and good afternoon, everyone, depending on you are across the globe. Before, we start this webinar with, solar, or electrical vehicle powered by, renewable energy, specifically with solar energy. I want to start with this statement, which is basically the cheapest energy is the energy you don't have to produce. I know with the global movement toward decarbonization and electrifying our home and businesses, there are a lot of opportunities and strategies out there that can reduce the energy consumption of your home or your facility. The first one is basically your building envelope. I mean, if you increase the insulation R value to exceed, the minimum code requirement, you will be saving a lot of energy to your building envelope. Upgrading, your window from single pane to double pane or triple pane, depending on the geographical region where you are located, can also further reduce your energy consumption. Increasing the daylighting when it's applicable and cost effective also will reduce your energy consumption. Optimizing the sequence of operation of your system, including HVAC system, will definitely reduce your energy consumption. And of course, replacing the equipment and appliances that have exceeded their useful life will definitely reduce your energy consumption. So these are the strategies can truly reduce your energy consumption across your home and your facility before even embracing and going solar and driving an electrical car, because the aiming here is to reduce the energy consumption so your solar system will be smaller compared to a home that consumes more energy that is not needed. So these are the outline that we will be addressing today. We'll give a little snapshot regarding the history of electrical cars, followed by, the acronym used in the field of electrical vehicle. And also we will talk about how, electrical vehicle operate. We'll talk a little bit more about, the electrical vehicle supply equipment. In addition to that, we'll talk about the emerging technology right now, which is a bi-directional EV charging and discharging equipment. And lastly, we'll go through a calculation example on how to size your solar PV system as well as solar energy storage to basically power your electrical vehicle. As you can see, from this slide, these are electrical cars that date back, to early 1800s. So electrical vehicles are not something new. They have been here for quite some time. And you can see just the level of workmanship, and detail that's being put, to build these cars. The bottom middle picture, as you can see, is the lady with her, carriage and with her, charging station. Basically, it is a battery that charges another battery. So the charging system has been, a while, since early 1800. It is nothing new, but the new system that we are witnessing lately, they are more advanced compared to the one we had in the 1800s. So these are the acronyms that you may find, when you are dealing with electrical vehicle, as you can see from here. So an electrical vehicle, any equipment that basically can use, electricity, and there are numerous, pieces of equipment that use electricity as a vehicle, from truck, vans, the buses, automobile, even a motorcycle can use electricity. In addition to that, they do not basically emit any combustion byproduct, through a tailpipe. The next one is the electrical vehicle supply equipment. These are basically the cables that comes with the electrical vehicle. So one side connects, to a power outlet or to an electrical distribution panel. The other one connects, to the vehicle. It is not a charging system, but rather, a communication device and a system that can transfer the power, from the source to the vehicle safely. The third one is the range, which is basically how many miles can you drive, with a fully charged battery. And next one is MPGE, which is the mile per gallon of gasoline equivalent. And the last one, this is a very important point that you need really to remember, that 1 gallon of gasoline, it has an equivalent energy content of 115,000 BTU. When you convert that one, it is 33.7 kWh. We'll be using this number as we move forward. This is basically a typical, electrical car with different components. This is by no means are all the auxiliary components for an electrical car, but basically, these are the major ones that you will witness almost in any electrical car. And we'll go through each one of them as we move forward. Here is, just move this window. Basically, what we are looking at right now, going from the right hand of your screen, that is your power outlet. For North America, we use 120 volt for single phase and for residential application, and 240 if you have two phase. 208 is for commercial application. From the power outlet or from the electrical power distribution panel, it goes, to your electrical vehicle supply equipment, in which it has some electronic component in there for supplying and monitoring the charges. Then it goes to your connector, what we refer to as J1772, which is basically the standard that we will be discussing, shortly. And then it goes to the inlet of your electrical vehicle, all of these from the power outlets of the electric or the electrical distribution system all the way to the inlet of your car, it is an AC current, alternative current. From there, it goes to the charger where it is converted from AC current to DC current. And then it goes to charge the battery. So the charge that goes to the battery, it is 100% DC current. So this is basically how it goes using your electrical vehicle supply equipment to basically charging your car. Common one is basically all electrical vehicles. Sometimes they are referred to as battery electrical vehicle because they are relying of 100% of the power to come from the battery storage system. Some cars, they have one single electrical motor. Others, they do have two electrical motor, one at the front and one at the back. And the battery that store energy to drive the electrical car, it is roughly between 350 to 800 volt. It is basically a high voltage. Also, as you can see from here, when you have an electrical vehicle, there is no fuel distribution system, meaning you don't have fuel pump, neither fuel line or fuel filter injector, as well as the fuel tank. So the first component that we will be talking about is the electric traction model. Basically, that is the replacement or the equivalent of the internal combustion engine. And it is usually an AC, a three-phase AC motor that is synchronized motor with permanent magnet. It is fluid cooled because we need to maintain the temperature requirement, the minimum, maximum as per the manufacturer requirement. And those system or the cooling system, some of them, they use, a heat pump system, other they use a fluid through basically a radiator that dissipate, the heat, at the front of the car. The following item is the power electronic controller. As you can see, the blue one on the left-hand side, and that basically manages, the flow of electricity, from the source, to the car, but also does control the speed and the torque, to your car to drive those wheels. Following item is or component is DC to DC converter. This component takes the high voltage from the battery pack, the large one, which is the yellow here from the picture, and basically reduce that voltage from 350, 800 to 12 volt. And 12 volt will be used for auxiliary component within the car system, and which we will be discussing in the next couple of slides. The following one is the thermal system. As we mentioned, there are several components in here. I'm just mentioning the major one, which is the traction battery pack, which is the yellow one, the electric traction motor, the onboard charger, DC to DC converter, and the power electronic controller. All of these components or blocks are, fluid cooled, and that fluid goes to like a small chiller, which is based on a heat pump system. It cools that fluid and circulated through those 5 components to remove the heat, either during the charge and during the operation of the vehicle. So we are within the manufacturer temperature range. The following one is the battery auxiliary that basically provide, electricity to your lighting system, to your motorized window, radio, or navigation system, or any other auxiliary component within your electrical car. Following one is the onboard charger. Basically, this one is a combination between an inverter, and a charge controller. And it does really communicate between your electrical vehicle and the electric vehicle supply equipment, just to ensure that your battery pack, which is the larger one shown in here with yellow color, not overcharged, neither undercharged, and to monitor also the current as well as the temperature. The following one is the transmission, which is basically, it is the transmission device that reduce the speed or increase the speed. It is part of the electrical motor. This device is also cooled through the system, through the cooling system. The following one is the charge port, which is basically where you connect your electrical vehicle, supply equipment from the wall outlet or your electrical distribution system to your car to charge, the battery. Following one, this is basically the traction battery pack is the equivalent of your fuel tank in an internal combustion engine. So the larger the battery with kWh, the more mileage that you can drive within one single charge. And there are different types of technologies out there that being used right now in electrical vehicle industry. These are the standards that being used right now in electrical vehicle, industry. One of them is the J1772 standard, starting with type 1, which has 5 pin, as you can see from the left-hand side. If you are connecting your vehicle, to 120 volt, that is considered a level 1 AC current. Between L1 and N, you have 120 volt. You connect it to a power outlet of 120 volt. If you do have 240 volt for residential, in this example, or North America, or 208 for commercial application, then you have L1 and L2 that will give you level 2, meaning you can charge your vehicle a little bit faster because you will have more power. The next point, which is PP, which is the proximity pilot. This one, it tells once you plug your electrical vehicle supply equipment to the power source and you connect it to the vehicle, there is a communication that takes place through the electrical vehicle supply equipment and tells the car basically to disable itself or being moved by the driver. So this is a safety feature for electrical vehicle. The following one is the control pilot, which is basically a communication line between your electrical vehicle as well as your electric vehicle supply equipment that can basically initiate, the charging of your electrical vehicle. It can carry other information as well. The bottom picture, and specifically the one on the left-hand side, is the 5-pin, connector adapter that can be used with another, charger that's commonly used right now, which is NACS, connector. We'll talk about it later on, which will be used widely moving forward. Next one is the 7-pin connector. In addition to level 1 and level 2, the bottom connector, which is DC plus and DC minus, those are the polarities, the positive lead on the left-hand side and negative lead on the right-hand side. These are what we call the DC fast charging, meaning if you have a DC source, you can basically power directly your battery pack within your electrical vehicle, and you don't need to go through the process of going from AC to DC and then from DC to AC. CCS stands for Combined Charging System. This is another standard for electrical vehicles. This is a summary basically of what we have discussed, but I want to talk a little bit more about the standard J1772 of 2017. When the standard appeared in 2017, it did list, 4 levels of charging: AC level 1, AC level 2, DC level 1, and DC level 2. It was considered AC level 3, in the previous, J7072 standard, but it was never implemented. And still, sometimes people, they get confused. DC fast charging, protocol or connector to AC level 3. There is no AC level 3. As you can see from the bottom in here, the text highlighted in yellow, this is based on North America NFPA, specifically NSC, standard article 625.41. The branch circuit has to be sized at least 125% of the maximum current, continuous current. In this case, if we go to AC level 1 on the left-hand side at 120 volt, single phase. So you have 2 options in here. If you have a circuit breaker of 15 amps, the maximum continuous amps that you can draw to charge your vehicle with level 1 is 12 amps. If you do have a 20 amps, circuit breaker, the maximum continuous current that you can draw is 16 amps. On the right hand side is a simple calculation. We know that the power is the voltage times the amperage, and it will give you the power in watt, and you convert that one to kW. AC level 2, 208 is for commercial here in North America, and 240 is for residential. So if we go with 208 and we have a circuit breaker of 30 amps, then the maximum current that you can basically draw is 24 amps. On the other hand, if you have 240 volt and you have a circuit breaker of 100 amps, then the maximum continuous current that you can draw is 80 amps. Both of them, the first one at 208, the maximum power is 5 kW, and for 240 is 19.9 kW available power unit to charge your electrical vehicle. Now let's talk a little bit about the DC level 1, which is basically you have a voltage between 50 and 1000 volts. If you compare it to the previous one, AC 1, level 1 and level 2, it is a higher voltage. If you have a circuit breaker, in this case of 80 amps, so the maximum current that you can draw is 80 amps, and second one, level 2, is 400 amps for basically large systems. So the key in here, depending on the level that you have, the charging level you have, the charging time will depend. It's going to run from 20 minutes all the way to 20 hours. And all of this depend on the type of battery you have, the type of chemistry of your battery, the state of charge or discharge of your battery, the capacity of your battery, if you have a larger battery versus smaller battery. All of these can impact, how much time it would require, to charge your battery. Next EV charging standard is CHAdeMO, which stands for Charge to Move. It is basically a DC fast charging, connector for very large power between 50 kW and 400 kW. It is basically competing with CCS connector right now. and the latest one, which is North American Charging Standard, that it's becoming very popular, and most likely it will dominate, the electrical vehicle charging equipment going forward. They are expecting that this one will be widely used, starting in 2025. Some vehicles already have, this type of connector, based on this standard. One of them is Tesla, and you can see it, the difference between CHAdeMO on the left-hand side versus an ACS on the right-hand side, and that one is the one that is currently used by Tesla vehicles. This is another standard. This is an emerging technology right now, what standard 15118, which is regarding bi-directional electric vehicle charging and discharging standard. So what is a bi-directional electrical vehicle? Basically, it is a technology that helps you to basically receive and share, a power to and from an external source of power. How does, bi-directional charging work? So basically, there is an onboard charging system that enable, the power movement between the source and the vehicle and vice versa. And lastly, the smart charging is a technology out there right now. You can have an application and you can program your electrical vehicle to basically charge at a specific time of the day, depending on the rate structure you have for your home or your facility. If the electricity rate at night is cheaper than the day, you can basically program your vehicle to charge at night, so at least the cost will be less charging your vehicle at night versus during the day. These are the type of bidirectional charging system. In this case, vehicle to home, V2H. Basically, you provide power from your electrical, vehicle battery pack, to your home through, provided that you do have the right infrastructure to support, of course, this concept in here. But there are certain vehicles are currently available in the market that can accomplish vehicle to home power. Following one is vehicle to load. Let's see, if you go out and you are camping, for example, you can basically use your electrical car as a mobile energy storage system, and you can plug it in, have a power strip, and you can plug whatever load that you have, refrigerator, TV, or any additional load. The following one is vehicle to vehicle. So basically, spare the capacity from another vehicle to your vehicle. And lastly is vehicle to grid, that can basically provide power from your electrical vehicle to the grid, and again, depending exactly if it does make economic sense to do that. You can have extra car if it's not in use, and you can pump, the power back to the utility grid. All depends if it does make any economic sense. So will bidirectional charging affect the battery life? Yeah, there are large studies out there. They mentioned that if you use your battery very often, back and forth, definitely will decrease the life expectancy of the battery pack within your electrical vehicle. A battery, it has a memory. You know what I mean? The more that you charge and discharge the battery, the less life expectancy you would expect, for your battery. It is better to charge your vehicle as little as possible. And we'll talk a little bit about our example later on. On the other hand, the University of Warwick found that managed use of vehicle to grid could control battery degradation. And lastly, as you can see in here, using your electrical vehicle battery, to power the grid or use it as a bidirectional very often may contribute, to decreasing the life expectancy of the car battery pack. These are the type of what we call standalone system. For those of you who are familiar with standalone solar PV system, they are not connected to the utility grid. You can see the solar PV array underneath the panel. You have the battery pack with the charge controller, basically as an inverter, as well as charge controller. And at the bottom, on each side, you have the electric vehicle supply equipment. So each one of these standalone solar PV can basically serve two electrical vehicle, and they come in different sizes regarding the battery capacity, depending on your application. If you are using it for cars, or if you are using it, for trucks or large vehicle, so they come with different sizes. This one is basically one of these is a closer look, and we'll be using this electrical vehicle in our calculation example. And as you can see from here, so basically this specific standalone PV system or charging system has a capacity of 4.4 kW solar array. It has a battery capacity that can hold up to 40 kWh of energy, and the range that can be used basically if your battery is fully charged can go up to 265 miles per single charge. The following one is a different type of standalone solar PV system. Basically, you have the solar array, and at the bottom you have the energy storage system. And this specific one can basically serve for electrical vehicles. The following one is a large, solar PV carport that can be either as a standalone system with a battery storage system installed nearby, the carport, or can be a hybrid system, meaning you can have the solar PV system, the battery, but as well as connected to the utility grid. So if you have an extended period of forecast, for example, that you don't have sufficient, solar rays, then you can basically use the utility grid. But these are becoming more popular, large solar PV carports converted to electrical vehicle charging station. Basically just add, a battery storage system installed somewhere, and the output from the PV system goes directly, to the battery to charge those battery. Or you can basically, if during the day, you can tap directly to those green electrical vehicle charging system, and you can charge directly DC from the solar array directly to your electrical vehicle. This is what we call a hybrid solar system. For those of you who are involved with the solar PV system, there is what we call grid-tied solar system. It is connected to the utility grid without any battery storage system. A hybrid system, basically the way it operates, if we start from the left-hand corner, So you have the solar PV array, the sun, strikes those solar PV array, electricity generated in the form of DC current, then it goes to your hybrid inverter, basically, and convert the DC current to AC current. So if there is a demand, for your home or your facility, then the electricity generated from solar PV panel can serve first in your home or your facility. Any extra energy will go second to your energy storage system. And if both of them are satisfied and you still have extra energy, then it goes to the electric grid. We have what we call bidirectional meter that register how much electricity is drawn from the utility grid and how much electricity is being put, back to the utility grid. And the utility company at the end of the year will send you a check if you have generated more power than what you have consumed. The battery, as you can see, it has two arrows back and forth, going, upward, meaning that when the battery is basically pouring electricity back to the system and serving your home. This is most likely at night, when there is no sun, you need to get energy. The battery can put the electricity back to your hybrid inverter and then supply your home. But at the same time, for the arrow going downward, it gets the power from solar PV panel to the hybrid inverter. And then from there, it goes directly to your battery. Once it is satisfied, as I mentioned earlier, that power will be converted from DC to AC and then injected to the electric utility grid. Now let's move and talk about a typical car, and this is a 2023 mid-size electrical vehicle American car. I want to mention that there are plenty of incentive, not only for electrical vehicle, talking about North America, but also for your electrical vehicle supply equipment, for your solar PV system, or upgrading even, the insulation, having your going from mercury type, thermostat to digital thermostat. There's plenty of incentive out there, even having, a heat pump system. There are plenty of incentive in here to help, homeowner and facility owner really to reduce, the use of fossil fuel and shift away to electricity as a source of energy. So in this specific application, we have a 2023 mid-size electrical vehicle. So in addition to the federal tax credit of 7,500, you have a state, tax incentive, tax credit for New York. It varies exactly where you are with your basically how much money you make per year, and basically that one will tell you exactly how much incentive or tax credit you will get. For this car, the maximum range that we can drive is 259 miles, per fully charged battery. It is a front wheel drive, meaning it has only one electrical motor. The acceleration, meaning going from idle, position to 60 mile, per hour speed, is within 6.5 seconds. That's amazing. The torque, basically, which is the force that you need to rotate those wheels, is 266 feet-pound, and the top speed is 148. I don't believe we we can drive 148 based on the road, regulations. The powertrain, which is the motor, is 150 kW or 201 horsepower. The battery type for this specific car, it is an absorbent glass mat, which is an AGM. for this specific manufacturer. I believe they are considering second quarter of 2025, they will shift back to lithium ion ferrophosphate battery, which is a better technology than AGM. Again, this battery has a capacity of 65 kWh. It has an onboard charging module of 7.2 kW, meaning even if you have the capability of having more power outside, the limiting factor for any electrical car is what is your onboard charging module. If you have 7.2 and you want to put 50 kW, is not going to help you much, because the limitation is how much power your onboard controller can push. EMCG, as we discussed before, is basically how many miles can you drive basically on the equivalent of maximum power that you can basically use to drive, in this case 131 mile in the city and 109 in the highway, so the average is 120. And if you recall, 1 gallon of gasoline here in the United States is equivalent to 115,000 BTU, British thermal unit, which is equivalent to 33.7 kWh. So in this case, when you do the conversion, I can drive 100 miles with this car, with this specific car, using 28 kWh to drive that car. Okay. So if I am using level 1, I will be charging my battery an equivalent of 4 miles per hour if I use level 1. If I use level 2, I will be adding 39 miles per hour. And lastly, if I use DC fast charging connectors such as demo or CCS or NACS, I can add 100 mile within 30 minutes for this specific car. Following one is basically we need to calculate how many miles you anticipate to drive annually using your electrical vehicle. Second is divide the number calculated from above by your electrical vehicle mile per kWh. The third step is to take your home or your facility annual electrical energy requirement, including your electrical vehicle or vehicles load. The fourth step is to calculate the daily electric energy requirement including your electric vehicle load. The fifth step is find out exactly, this is really very important, is to find out what is the average annual solar radiation, what you usually refer to as sun hour per day. In this case, for Garden City, New York, so the average solar radiation is 4.76 kWh per square meter per day, meaning for each square meter of your solar PV array, you can receive 4.76 kWh of energy per day, and you do the math. So we choose in this application for the solar PV array to serve our home and our electrical car. The solar PV system will be tilt angle of 45 degree, and the azimuth angle is 180 degree. 180 degree, it is a true south exposure for the solar PV system. For the northern hemisphere, where United States is located, to maximize your energy, harvest, and consequently the energy production through your solar PV system. The best, orientation of your solar PV system is to be at true south, meaning at 180 degrees. On the other hand, if you are on southern hemisphere, let's see, if you are in Australia, it has to be at true north. So depending on the geographical region where you are located, just keep that in mind. And lastly, number 6, divide the calculated value from step number 3 above by the average annual solar radiation value from step 5. Now we'll go through, a calculation example. So in this case, if I am driving my car, back and forth, to work, and I'm only, a round trip is only 30 miles per day or 40 miles per day, I believe 15,000 mile, per will be more than enough, because most likely I will be using it less during the weekend. So if you take 15,000 mile per year and you basically divide it by the range of that specific car that we saw before, which is in this case 3.98. If you go all the way at the bottom right here, the range over the battery capacity. So, the range is 259 for this specific car, and we divide it by the battery capacity, 65. So in this case, the range is 3.98 miles per kWh. So the next step, which is step number 3, is to add both. I'm taking home as an example. You can use it for your facility as well, wherever the application that you have. Number 3, I'm taking 7,300 kWh as an annual home load. It is an average of 20 kWh per day for my home consumption. Plus, I have 3,768 kWh, which is the annual load to drive my electrical vehicle. So the overall energy requirement to satisfy both my home as well as my electrical vehicle is 11,068 kWh. I take that number from step number 3 and I divide it by 365 days per year. That will give me the average daily energy required to basically supply energy to my home as well as charge my electrical vehicle. Then we'll move on to step number 5. We take that number calculated from step 4 and we divide it by the solar radiation for my location. In this case, for Garden City, 4.76 hour per day. Remember, solar radiation we refer to as the solar sun hours. In this case, my solar system is 6.37 kW. Again, step number 6, because solar system are not 100% efficient. There are a lot inefficiencies within a solar system, from a mismatch, to power losses, to your cabling, to dust over your solar PV panel, to the inverter and charge controller inefficiencies. All of those, they reduce the overall capacity of your solar system. In this case, we applied a factor of 20%, inefficiencies. So you take the number from step 5 and you multiply it by 1.2 to take care of the inefficiencies. So in another way, you need to oversize your system to achieve the required 6.37. In this case, my final, solar PV capacity should be 7.64 kW system in order for me not only drive my electrical vehicle 15,000 miles per year, but also to satisfy the load of my home, which is in this case 7,300 kWh. Following one is to go through sizing your battery. Let's see, you have a roof, you have plenty of roof area, you can install, 7.6 or 7.7 kW system over your roof. Then you gotta make a decision right now, what are you looking for to cover with your battery system? And we'll go through the steps in here because there is no one solution for everyone. Depending on your application, the answer for you may be different for the other individuals. So let's go through the step that you need to consider when you sizing your battery bank. So number one is basically define your energy goals. What are you trying to achieve in here? Are you planning just to address your critical load during a power outage, or are you considering to provide the power for the entire home, or you want to be self-sufficient when basically the utility grid is down? Number two is to determine, the size of your load. Once you crunch those numbers and you determine your load. Number three is to choose how long you want to be sustained using your energy storage system, what we always refer to as days of autonomy. And this is depending where you are, depending, of course, of the reliability of your electrical utility grid. If you have a large power outage, during during the year, you may want to go to 3 or 4 days of autonomy. And if you have a reliable utility grid, 2 days may be more than enough, or even 1 day may be more than enough. I mean, where we're living here, I believe the average per year is probably 5-6 hours per year. So the system is really reliable. So it doesn't make any sense, to size your system, if you're larger than what you need, because the grid, reliability is very important. You need to understand the grid reliability, but also during an overcast, extended overcast, you want to make sure that you will have sufficient power to be provided by your electric utility grid. And all of that you can really estimated what would be the appropriate days of autonomy. And lastly, number four is find out the maximum battery bank depth of discharge. Depending on the type of battery that you use, the older type of battery like lead acid battery, they don't like to go more than 50% depth of discharge. Regarding new technology, lithium ion batteries, you can go down to 90% depth of discharge without any problem. So that will have an impact on the capacity of your battery that you need, to charge basically your electrical vehicle, as well as providing power to your home at night or during an extended, overcast in your area. I don't know what happened. I had one slide in here. Here we go. I'm sorry. And that's done. I had one slide. I don't know what happened to it. Let me see if I can find it. Look for it and send it to the group. Most likely I have it in the other file, but Let me just go in here. With that, I believe the presentation is concluded, and I'm gonna open the floor right now, for any question from the audience.
Great, thank you so much, Khalid. It was very interesting. I really liked it. I really enjoyed your presentation. Um, Please leave your comments in the chat if you have any or anything that you would like to discuss. I would like to ask some things to get things started. I would like to ask you actually if you know if there's any possibility to include PVs onto the vehicles themselves, or are there any existing vehicles like that in the market, and what are the main challenges to that if we would go with that approach to have the solar PVs on the car itself?
I saw a couple applications right now, but they are not commercially available. They are using the thin film technology, basically, to be part of the car body. But the power basically is very minimum that will not be able to sustain the battery, regarding, the capacity needed, to drive the car for an extended period of time,
Okay.
but it is not, commercially available right now.
Mm-hmm. Okay, I understand. So, like because of the flexible PV, they would have like lower, or the area is not enough. Would
It
that
is
be,
not enough.
would it be possible to have it on bigger vehicles like trucks maybe, or something like that, that we could maybe have silicon PV? You think that would be a better application?
You can have it, but I do not believe it will really provide you the capacity needed to drive, for
Okay.
a longer range,
Mm-hmm.
because of the area and the efficiency. As we know, thin film technology versus polycrystalline technology, there is a huge difference in efficiencies. For polycrystalline technology right now, you can go probably up to 23% versus thin film technology, probably around 17, 18%.
Mm-hmm. Okay, I understand. So what do you think is or how do you think that electric vehicles will play a role in the decarbonization of our cities in general? Do you think that the building vehicle to grid will be one of the main contributions in decarbonizing our electric grid?
Things that I want to mention regarding the electrical vehicle and the benefits of electrical vehicle. When you drive an electrical vehicle, even when you plug your electrical vehicle to a power outlet that basically generate electricity from a central power plant that use fossil fuel, for example, you still contributing in basically reducing the impact on the environment, because locally you are not basically exhausting byproduct, from an internal combustion engine, because you will be driving an electrical vehicle. The combustion, byproduct will be at the central utility company that can be managed more efficiently at the central plant, rather than basically exhausting those fumes while you're driving in your community or in the city. So definitely it will have a positive impact driving electrical vehicle versus driving an internal, combustion engine. Regarding the second portion of your question, having your electrical vehicle, to put the power back to the utility grid, it has an advantage, and the advantage is, of course, to reduce, the impact on the utility grid at night. During the time when there is more demand, the people who are driving electrical vehicle, can basically inject the power needed for other, consumer that are connected to the utility grid. So the utility grid does not need basically to upgrade their system to a larger grid to satisfy those energy demand. more than that, providing the power, from your electrical vehicle to the utility grid based on the technology we have right now. And as we mentioned, I believe in one of two slides, we gotta really be very careful, how often, to charge and discharge your battery. In the example that we are looking at right now, if I am driving, 15,000 miles per year, and which is an average of 40 miles per day, I would rather wait until the end of the week and charge my battery once a week. So the rule of thumb is 20-80, meaning don't discharge your battery more than 80%, and consequently don't let it more than 20%. So always, even if the manufacturer is saying you can discharge it down to 90%, leave it at 80% and charge it as few times per week as possible, because that way you extend the life expectancy of your battery. The manufacturer right now can provide up to 7-8 years of warranty for your battery, so you don't need to worry about it, provided that you follow the manufacturer recommendation regarding charging and discharging.
So do you think that one of the main drawbacks now today is the battery issue, and with vehicles, what would be some, or do you think that it's like we're there and we can switch to electric vehicles altogether? How do you think that our state now is as a technology and science?
Based on the current research and development in the battery industry, there is what we call right now solid state, energy storage system, which is really a very promising technology that most likely we will be able to pack more energy in a small footprint compared to what we have right now. And this is, if you compare the old technology, lead acid battery, and they still in the market right now compared to lithium, ion battery, there is a huge difference. Lithium ion battery, you can discharge it, down to 90% without any problem. But for lithium, for lead acid battery, the maximum, I believe, depth of discharge is 50%. So the technology is very promising with solid state battery, and I'm very optimistic in the next couple of years, probably something will start being available commercially on a larger scale.
Okay, great. That's really interesting. I'm excited to see how we change our whole like system, electric the electric grid and our transportation and yeah. So I don't see any comments, other comments in the chat. So if there's not any questions, I think we can conclude our webinar. Thank you so much, Khalid. It was really interesting. It's one of the first presentations that I've participated in electric vehicles, so I learned a lot. Thank you very much, and thank you for your time and putting your effort into this. Yeah, so thank you everyone for participating in the webinar yeah, please visit our site, our LinkedIn on the TC6.7 Solar and Other Renewables on ASHRAE. We have a LinkedIn page, and we will also be posting the recorded webinar on our YouTube page. So yeah, thank you very much.
Sure.